not end up with 2 tests on the same day. This is hard enough as it is. And you know that you have to watch the special senses lecture on your own time. I think it's available to you now. I hope that it is. You're supposed to have a test after we finish this lecture. So let's see how long it takes me to finish this lecture today. If we could actually move up a little bit, that would give you guys a little more breathing room. And so I'm not going to rush it by any means, but I want you to know that because of all of this stuff, the schedule has to be a little bit flexible. So last time, we were saying that the posterior portion of the cord is sensory, and the anterior portion of the cord is motor. Now, if you look at the neurons that are in the cord, you'll see that the visceral sensory neurons are here closest to the center, and the somatic sensory are a little closer to the periphery of the spinal cord. SS stands for somatic sensory. Soma means body. So sensation from your body parts is out here, whereas sensation from your viscera means organs, visceral sensory is here. And then anterior portion of the cord, which is the motor portion, the visceral motor neurons are here, and the somatic motor neurons are there. Now, please remember that long fibers, long processes, long dendrites and long axons really have to be myelinated in order to get impulses rapidly enough from one end of the process to another. So long processes you can expect to be myelinated, and thus you can expect long processes to be white matter. Little tiny microscopically short neurons and short processes are non-myelinated, and they are gray matter. So going back one slide, you can see that the outer portion of the cord is white matter. Thus, the outer portion is long myelinated tracts. What's here in the gray matter of the cord? Short, non-myelinated neurons. Now, we have neurons in our tracts, in our cord, that run up to the brain, and those are ascending tracts. We have tracts in our cord that go down from the brain. Those are descending tracts. And then we have tracts that go from one side of the cord to the other, and those are called transverse tracts. That's pretty straightforward. What I would like you to see, let me show you here. This is a really clinically relevant and clinically significant slide, because what they've done with the spinal cord in this slide is they've colored ascending tracts, that is, tracts that go from the cord up to the brain. They've colored those blue. And descending tracts, which are the motor tracts coming from the brain down to the cord, those they colored red. So you can see that the posterior cord it's all ascending tracts. So sensory information comes here. Sensory information comes in, goes into the dorsal part of the cord, and then tracts go up the dorsal portion of the cord to the brain. You see there's also some ascending tracts laterally, but they're not, they're not huge. They're not as big as this. And there's even a couple of ascending tracts anteriorly. The descending tracts, the motor tracts from your brain to your cord, are primarily anterior, although you see there are some lateral motor tracts as well. Now, why do I say this is so important? It's so important because people get spinal cord injuries. If a person has a posterior cord injury, they will injure their ascending tracts. Thus, you can expect that person to have lost sensation. If a person has an anterior cord injury, it's mostly motor descending tracts that would be damaged, and that person would be paralyzed. They would be unable to move. You can see that lateral cord injuries are a mixed injury. There's some sensation lost in the ascending tracts, and there's some paralysis from the descending motor tracts. These cord injuries, the clinical aspects of these cord injuries, are 100% predictable if you understand where these motor and sensory tracts are found in the cord. Now then, ascending pathways, ascending tracts are composed of 3 neurons. You may think that, when you think about cells, you think about them being microscopically small, but please remember that neuron processes can be extremely long. Yes, there are microscopically short neuron processes. They are all gray matter. But these white matter tracts, they are long. So we end up with only 3 neurons, 3 cells that provide all of your ascending pathways. And I think this easy thing for me to do is to just show you a picture, and that will help you to understand. So let's look at this touch receptor in the bottom of this foot. The touch receptor is attached. It's basically a long dendrite. And this long dendrite goes from the bottom of your foot all the way up your lower extremity to your lumbar or sacral spinal cord. That's incredibly long. And then it branches. This same dendrite has a branch into the gray matter of the cord, but the rest of the dendrite, same cell, ascends through the entire length of the spinal cord to the medulla. That is one cell. Incredible how long that one dendrite is. Now that's a unipolar neuron. There's the cell body out here, but that's just basically one long dendrite. We call that first dendrite a first order neuron. Remember that the overwhelming majority of decussation, which is crossing over, occurs in the medulla. So this first order neuron, this very, very long sensory neuron, long sensory dendrite, has a synapse, the first synapse on its way to the brain. The first synapse is in the medulla. A second order neuron starts its nucleus and body in the medulla and decussates and goes ascending to the thalamus. So that is a much shorter, but it's still long. It goes from the brainstem to the thalamus, so it's still white matter. It's myelinated. And in the thalamus, there is a synapse. And from the synapse, we have what's called the third order neuron, which goes to the primary sensory cortex of the brain, which I hope you all remember is the post-central gyrus. So 3 neurons, a first order neuron, which is incredibly long, a second order neuron from the medulla up to the thalamus, and a third order neuron from the thalamus up to the post-central gyrus. Georgina, would you please mute your mic, because we're getting feedback from it.
Oh, it was on mute without me.
I don't know what she said.
I said it was on mute without me doing it. When somebody was coming in and then it's just on mute. I don't know why.
Okay. Well, it's okay. It's all right. But if you'd be kind enough to mute it now, I'd appreciate it. Thank you. All right. So an ascending pathway. I'm going to go back to the previous slide. An ascending pathway is 3 neurons. Here is a different one. This is a proprioceptor, a stretch receptor, and it's in the muscle. And there is a long sensory dendrite from the muscle to the spinal cord, where in this case there is a synapse, and the second order neuron ascends all the way up. Oh, look, it went to the cerebellum. Remember I told you that the cerebrum, the left side of the cerebrum controls the right side of the body, but the cerebellum fibers do not decussate. They do not cross over, so that balance in the cerebellum is ipsilateral. And here's a perfect example of that, going backwards again. Balance is only 2 neurons until we get, it's a first order neuron, a second order neuron, up the cord to the cerebellum, and then there's a short third order neuron there in the cerebellum. So that's how ascending pathways work. Everywhere there is a synapse, we have a synaptic delay, because we have to have the chemical, the neurotransmitter, move across the synapse and stimulate the next neuron. If we go back to this slide, you'll also see that this dendrite had a branch to the gray matter of the spinal cord. And you're going to see that while this information is heading on its way up to the brain, something else is going to be happening here in the cord, and we're going to talk about that in a few minutes. Now, the thing I want to tell you, I've mentioned before that the overwhelming majority of decussation occurs in the medulla, but I said some decussation occurs in the spinal cord. This is an example of that. Temperature and pain receptors actually they decussate in the cord itself. So here's a pain receptor. The long dendrite goes from your hand, in this case, all the way up to your cervical spinal cord. There is a synapse, and then the second order neuron decussates right there in the cord. The crossing over is in the cord instead of in the medulla, and that second order neuron ascends again to the thalamus, where there's the synapse, and the third order neuron goes up to the primary somatosensory gyrus, which is the post-central gyrus. The descending pathways carry impulses from your brain, motor impulses from your brain, down your cord to your body. And we have two pathways when we talk about that. We have the direct ones and the indirect ones. The direct ones are pyramidal, and the indirect ones are all the other tracks. Let's see what he's talking about. Now, the one thing about the, remember, ascending pathways are two neurons. Are three neurons. A first-order neuron, a second-order neuron, and a third-order neuron, okay? Descending pathways are only two neurons. There's only two neurons, and we call them the upper motor neuron and the lower motor neuron. So let's look at an upper motor neuron here and see what it does. Here is a neuron which starts in your brain at the precentral gyrus. Remember, that's the primary motor strip. And this long axon travels down through your brainstem. It decussates in the medulla, and then down the entire length of the spinal cord. Down the entire length of the spinal cord. It has a synapse here to a little tiny microscopic gray matter neuron called an interneuron, and then another synapse to the long lower motor neuron that goes out to your muscle and says, move. Some of these, I'm going back now, some of these actually don't even have the interneuron. Here's a tract that starts in your brain, goes down. It decussates way down in the cord itself, but it still decussates. And then the lower motor neuron goes out to your muscle. So the point is, upper motor sensory tracts have three neurons. Motor tracts have two. This little inner neuron, we have to think about it, but for all intents and purposes, we talk about in motor tracts an upper motor neuron and a lower motor neuron. That means that there's only one synapse when there's only an upper and a lower motor neuron. There are two synapses for sensation. That means sensation is a little slower to get to your brain than the motor commands are to leave the brain, because everywhere there's a synapse, there's a slowdown. There's a little synaptic delay. There's only one synapse for motor and two synapses for sensory. Here's an example of an indirect track. Here's one starting for gross motor movement or for smooth movement. So it's starting in the red nucleus. It synapses right away in the medulla. It's not synapses, I'm sorry. It decussates in the medulla and heads down. Synapses here and heads out to the second lower motor neuron. Now then, what happens if we damage our cord? If you damage your cord in the sensory area, you have what is called a paresthesia. This word is an important word. You're going to hear it over and over again. It is a paresthesia, and a paresthesia is a sensory loss. Now, lots of our patients have paresthesias. If your patients who have type 2 diabetes will get severe atherosclerotic vessel disease in the little tiny arteries that give blood supply to these long lower motor neuron, or they would have atherosclerosis in the little tiny blood vessels that give blood supply to the sensory neurons, first order neurons. If those little tiny vessels that give blood supply to the neurons get blocked by atherosclerosis, then the person's nerves do not function normally. And especially if it's a sensory nerve, a first order neuron, the person will have paresthesia, sensory loss. And that feels weird. They will have strange feelings like burning, or when there's nothing hot, or itching when there's nothing to cause itching, tingling when there's no reason for them to tingle. Those are all paresthesias, and it's a sensory loss. The paralysis is loss of motor function. That's an entirely different thing than paresthesia, which is loss of sensory. This is loss of motor. All right, I'm going to stop for 1 second. There's lots and lots of discussion going on the public chat, and I'm trying to just glance over at it from time to time, and I realize that I should have started recording this. So with my profound apology, I will start the recording now. All right. If a person, now think about this and follow along. If a person has paralysis of the lower motor neurons, then motor impulses do not get to the muscles, and the muscles will just be flaccid. Flaccid means they're just floppy. They don't do what you ask them to do. They just sit there and they're kind of floppy. Flaccid paralysis is the result of injury to the lower motor neurons. And what happens is the muscles actually atrophy. They get smaller and they shrink up. So an anterior cord injury would result in flaccid paralysis, inability to move, but the muscles are weak and floppy. This is different than spastic paralysis. In spastic paralysis, the upper motor neurons are damaged, but the lower motor neurons from your spinal cord out to your muscles are still intact. If the lower motor neuron, which goes from your spinal cord to your muscle, is still intact, then the spinal cord, part of the central nervous system, spinal cord will continue to stimulate the muscle. The spinal cord stimulation of the muscle will have nothing to do with what the brain wants, because the upper motor neuron's damaged, so what's coming from the brain can't get down to the cord. So basically, the spinal cord just stimulates the muscle to contract all the time. If the spinal cord is stimulating a muscle to contract all the time, the person gets what's called spastic paralysis. The muscles go into spasm, and that's where they stay. Is no voluntary control of the muscle, because the upper motor neuron from the brain to the spinal cord is the neuron that tells the muscle what to do. That upper motor neuron is damaged, the lower motor neuron is intact, then the person's paralysis will be spastic. If a person has a lower motor neuron injury, so that nothing is going from your cord to your muscle, then the person will have flaccid paralysis. Cutting the cord, unfortunately, is a very, very severe injury. If you cut the cord completely, that's called transection. And everything that is innervated from that level of transection all the way distally will be lost. So paralysis and sensation, if you cut the cord completely, will be lost for everything distal to the transection. That's very severe. Transection between T1 and L1 is called paraplegia, because what happens then is if you cut the cord between T1 and L1, you lose sensation into the lower extremities. Paraplegia then is paralysis of the two lower extremities. If you cut the cord at the neck, then you lose innervation to both the upper and lower extremities, and that's called quadriplegia, which quad means four. If we traumatize the cord can swell up. If we don't have to transect it to cause a problem. If we traumatize the cord and the cord swells up, then the cord is in what's called spinal shock, and the person is just as paralyzed, but we hope that the paralysis can resolve when the swelling of spinal shock goes away. Now, I wish that I didn't have to talk about this. Because it's sensitive. I wish I didn't have to talk about this, but I do have to talk about it, and you have to learn about it. Although in the world of 2020, we have many and appropriate political sensitivities. We don't want to offend anybody, but I have to tell the facts as they are, and you guys have to learn them so that you understand. Poliomyelitis is a disease of the spinal cord. It is caused by a virus. It destroys the anterior ventral horn of the spinal cord so that the lower motor neurons are destroyed and the person develops flaccid paralysis. Now, this paralysis can extend up the cord so that ultimately we get to the neurons, the lower motor neurons that go to the lungs or to the heart, and then the patient will stop breathing. This is bad.
You are now unmuted.
So we got very close.
You are now
We got
muted.
very close to eliminating poliomyelitis. We got very close to eliminating it. When I was a young physician, because we have a very two different effective vaccines against polio, the Sabin vaccine and the Salk vaccine. I will never, ever forget, the Salk vaccine is an oral vaccine. It's not a shot, it's oral. And they would put the vaccine on a sugar cube. And everybody, we were kids, we loved this. We were kids, we didn't know what's going on. But I'll never forget being taken to school on a Saturday. Oh my God, we're school on a Saturday. All of us kids lined up, and they gave us a sugar cube to eat. I thought I died and gone to heaven. I never had a sugar cube in my life. And, oh my God, but that was my vaccine against polio. We almost completely eliminated polio in the entire world. And that would be a wonderful thing if we could eliminate polio in the entire world. We got very close to it. Unfortunately, in northern Nigeria, there were a group of imams who believed that polio vaccine was a plot from the Western world to give the children of northern Nigeria HIV, to give them AIDS. Now, there's a huge epidemic of AIDS in Africa, and in a person who was not well educated, it was easy to believe that this was a plot instead of just having to do with the normal way viruses are transmitted from one person to another. So these people would not vaccinate their children. So we had a concentration of polio in northern Nigeria that we couldn't, as a world health, we could not eliminate. The religion there involves making a pilgrimage to Mecca at least once in a person's life. That's called a Hajj. And so these people who many times were carrying the virus of polio would make a trip to Mecca in Saudi Arabia. Very, very close contact there. And the entire rest of the world had gotten rid of polio. And so many people decided they didn't need to vaccinate their children anymore because the polio wasn't there in their country. But polio was mixing in Mecca, and people from literally all over the world, but in large part it was persons who came from Indonesia and other sub-Saharan African countries and some Middle Eastern countries who would go to Mecca and be exposed to polio. They had not immunized themselves because they thought polio was gone, and polio resurged. And so sadly, we now have a resurgence of polio in the world because people didn't understand and wouldn't vaccinate their children.
You are now unmuted.
I just get horrified by this. Now, I have to tell you that normally in this class, at this point, I talk about polio a little bit, and I want to show you some video, but I have to go out of this briefing for a minute to find it.
Excuse me, Dr. Rizzo.
So question, Damien.
Have you ever seen anybody that was using the iron lung machine?
I have, and I was just going to show you that.
Oh, okay.
I was just going to show you that.
You are now
So if you guys will give me a moment, as you know, this program is not instant. So it'll take me a minute to find this video, but give me a moment and I'll find it. So I'm going off the, you can still see me, but I can't see you as I go to find these videos. Yeah, Damien, there's at the Centers for Disease Control, I have a good friend who is the head of intelligence for the Centers for Disease Control. And in my previous job before coming to Polk, we provided CDC with, and my organization, my former organization, still provides CDC with all of their intelligence. And one day I was down in Atlanta visiting him, and they had an iron lung in the lobby. It's a tragedy. This is a story of tragedy that we got so close to eliminating polio in the world, but we haven't. All right, let me find this briefing here. Give me a second. I got to stop talking so my brain will work in one direction.
You are now muted.
Now, when David was like 18, he set a world record for the most infinite tumbles done on a paramotor, which was like 200 something. Currently, I think the world record for the most tumbles on a paraglider is around 500 or 600. Now, David is trying to one-up and claim the world record for paragliding infinite tumbles. And in order to do that, what he's doing is actually jumping out of a skydiving plane with the paraglider at 23,000 feet. This is something that like no one really does. He's gonna go first at like 5,000 feet, jump out, the paraglider deploys, and this is just a proof that everything, his whole setup's gonna work. So 5,000 or 6,000 feet, we bumped up to 20.
Uh-oh. Oh, you're still there? Good. I thought I closed you off. Give me a second. I'm still working.
So far, he's done some infinite tumbles. Seems like everything's working real well. So,
Got a shot. Hi, buddy. But the way it looked, everything was in front of the line, so it didn't look like you would have good time.
Yeah, buddy. Woo! Paraglider, but that's kind of to be expected. 23,000 feet.
Maybe it's on this brief.
He started the infinite tumble, kept going till about 20,000, and then stopped. And right now we don't know why. I'm sure it's a very good reason, but
Something like that. I wonder why.
That was the problem? No, this is more or less is good, but this is heavy, and when it's like 6,000 meters, it's very, very fast, and this is like 8G or 9, and this is for me, so we do this impossible.
Reserve, a front mount reserve.
Take all that or...
It's
like this.
a skydiving reserve. Now, that's the best thing we could come up with for him to do it now. We obviously have paragliding reserves, and he had 2 of those, but those aren't certified to any FAA spec. However, the skydiving reserve is. So what he did was he wore a skydiving rig along with his paragliding harness, along with the oxygen and everything else, and 2 more reserves. But when he started doing the tumble, he's pulling like...
All right, so I'm going to share this picture with you first.
And the reserve weight on his chest...
Let me go back to where we were.
Like,
Where are you guys?
maybe 20 pounds of weight times 6 to 8
Where did you
kgs.
go?
It was like putting way too much force on his chest. So he decided to abort, which is obviously the right call. And we're going to come up with a better gear solution and go back and attempt the record again.
There we are.
Oh my goodness.
With the Scout, make sure
You unmute me again.
it's almost...
So I hope you can see this picture. This is a ward with children with polio and adults, children with polio. And these people are laying in a contraption called an iron lung. Because they are paralyzed, basically from the neck down. They can't breathe. So the iron lung is this airtight contraption. The people lay in it, paralyzed on a mattress. Their head sticks out of a plastic sheet that has a tight elastic band around their neck to keep the air in. And on the other end, there's a big rubber diaphragm. The big rubber diaphragm is attached to an electric motor. The electric motor pulls on the diaphragm, makes a vacuum in here, which causes them to inhale. And then this motor pushes in on the diaphragm, which causes them to exhale. And these people spend literally their entire life. This ward is so loud because all of those electric motors are working at the same time. Whoops, I didn't mean to do that. I meant to do this. Oh, come on. I'm trying to get to the, there we go. All right. Oops, I don't want that.
Diane Odell of Jackson, Tennessee, has lived in an iron lung longer than anyone still alive today. She owes her life to this device and has relied on it since contracting polio at the age of 3 in 1950.
And we were catching June bugs and putting them on strings, letting them fly around our heads. And I told her I didn't feel good, I was going to go lay down. I was up all night with a headache and my legs hurting. That morning I could not walk.
Soon, she couldn't breathe and was put in an iron lung. As a child in the 50s living in an iron lung, Diane had lots of company, as thousands of other children were in the same situation in hospitals from coast to coast.
They would push our iron lungs close together so we could play together. And our playing together consisted of our spitting at each other because we couldn't do anything else.
Doctors working in those hospitals still recall the constant hum of all those iron lungs operating simultaneously.
On the 3rd floor of Municipal Hospital, there was a ward filled with iron lungs, and the noise was deafening, and I hated to go up there because it was depressing.
You might think that after all these years, technology would have evolved to present Diane with other options.
For other people, there are other solutions. There are chest respirators that fit on your chest, but that's for people who have a straight spine. I don't. My spine is curved like an S.
And from her position in the respirator, this is how Diane sees the world, through mirrors, because she's been flat on her back, day in and day out for more than half a century. When Diane was diagnosed with polio and put in an iron lung, her parents, Geneva and Freeman Odell, never considered institutionalizing her. From day one, they were committed to caring for her at home, even though the experts of the day suggested sending her away. As they speak, you can get an idea of how loud Diane's iron lung is, day and night.
I think we've just done what most parents would do. I don't think I'd be alive if it wasn't for them.
But as Diane's parents get older, the question is, who will take care of Diane when they're gone? Her sisters are not equipped to maintain an iron lung. Today, nobody is. There are only about 30 people in the U.S. still living in iron lungs.
It's sad because these 30 folks who are still in iron lungs really got blown off. There was a company that was servicing the iron lungs, and it was bought out by another company. And the folks who were in the iron lungs were told by letter that the new company would no longer service their iron lungs, and they would have to go to a positive pressure ventilator. And some of them were not physiologically able to do that. So these poor folks who are in iron lungs are literally on their own.
All right, one last video, 1 second.
I'm Martha Mason. I live in a village, North Carolina, Lattimore. And I shall be 17 years old tomorrow.
Now listen. God bless you on their birthday.
It's very pretty. To me, this has become such a normal thing that I never think about it. I really never give it a lot of thought. It's called an iron lung, and that's pretty obvious why. It takes over for your diaphragm. It's like just a big can of air. I believe the last one was manufactured in 1977. There are other means of ventilation, and I've chosen not to do that.
Happy birthday.
Thank you. You make it a happy birthday.
Right.
Glad to see you too. It's been too long. My parents didn't want this life for me. There was an epidemic, and children were dying just fast. And I've often thought about, in retrospect, how my parents felt. You're their only son. They had just buried you. They were taking their only other child to the same place. Can't you just imagine how that was? It was assumed by people in general, and me too, that both my parents would outlive me. See, the doctor said at most they could think maybe a year. It was like, take her home, make her happy for a year. Or less. Well, here it is. A long time later.
You are now unmuted.
So I had a friend whose parents
You
did
are
not
now
vaccinate him, and he got polio when we were, I guess we were both about 11 or 12 or 13, and he got polio. It was a devastating thing. And polio should be gone in this world. I want you to think about this as we're social distancing right now for a virus that has somewhere between a 1% and 3% death rate. Polio was much, much worse. And until we had a vaccine, people just basically gambled with their life. And we did the same thing with all these other diseases for which now, thank God, we have vaccinations. I shudder at the thought of people who won't vaccinate their children. I just shudder at it.
You are now unmuted.
Excuse me, Dr. Rizzo.
Yeah, Damien.
What does the other type of breathing device look like? Can they...
Well, there's two ways to do it. One is you can put a respirator
You are
or
now
just
muted.
over the chest. It's a vacuum, and it's extremely cumbersome and very, very difficult. And it's very rare, actually. I've never seen one in real life. I've only ever seen them in videos and in pictures. But what most of these people end up doing is getting a tracheostomy, and they get put on a ventilator. And they sit at home on a ventilator. They sit up in chairs with a ventilator. Of course, you can't talk when you're on a ventilator. So when they have to talk, they take a breath from the ventilator, they unplug themselves, put their finger over their stoma, say, hey, I would like a sandwich, and then they plug their ventilator back in, and they suction themselves, because on a vent you have to be suctioned constantly. And so they sit there, they've got their ventilator to one side and they've got their suction machine on the other, and they take a breath and unplug themselves and stick their suction down their trach and plug themselves back in. Not for everybody.
You are now unmuted.
Yeah, that's pretty sad.
You are now
It's
muted.
very sad. It's very sad. And you know, it's sad and totally preventable. Totally preventable. It just breaks my heart. I mean it. Seriously, it breaks my heart. All right, amyotrophic lateral sclerosis is Lou Gehrig's disease. For those of you who have a short memory, you might remember from maybe 5 or 6 years ago, there was a fundraising thing nationwide, the ice challenge. They poured ice water on people's heads, and you raised money by pouring water on yourself or on each other, ice water, and donated so much money to try to cure amyotrophic lateral sclerosis. These people lose their ability to swallow, they lose their ability to breathe and to speak because of damage to the anterior motor neurons of their spinal cord. I have had a student at Polk State whose mom had amyotrophic lateral sclerosis and died from it. Now, when we test the spinal cord to see if it's intact, we have CAT scans, of course, and MRIs. But clinically, the thing you do is you test a person's reflexes. Now, I want to go past this. Normally, at this point, we are sitting in our classroom, and I would have somebody like Damien, who would always show up in shorts, and I would bring him up to the front of the room, and we would tap on his reflexes, and I would show you reflex arc. But we don't have that. So what I'm going to do is go over here to, hang on a minute. Let me get Google up. Here we go. Here is an example of a spinal reflex. And I want to make this bigger. Here's an example of a spinal reflex. Here's a hot thing. You're not supposed to touch that. So stupidly, somebody touches it, and the sensory dendrite carries the impulse up, 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 up to the dorsal aspect of the cord, which is the sensory aspect. Now, remember that neuron has a branch that goes up, up, up to the brain. But first, before that, this is still a first-order neuron. Before the sensation gets up to the thalamus or to the brainstem, even the brainstem first, there's a little synapse with an interneuron, which is gray matter, in the gray matter of the cord, and a synapse to a motor neuron, anterior cord is motor, to a motor neuron which goes out to your biceps and causes your biceps to contract and pull your hand away from the hot stove thing, that pot. Now, this is called a spinal reflex. It's called a spinal reflex because it is entirely contained within the spinal cord. Where in this spinal reflex, is the brain? The brain's not there at all. The brain doesn't even know this happened. Remember that the central nervous system is the brain and spinal cord. And here's the spinal cord ordering a motion without the brain knowing about it. Now, eventually, the brain figures it out, because remember that this first-order neuron has a branch that goes up to the medulla, and then there's a decussation, and there's a second-order neuron, and a synapse in the thalamus, and then we get the third-order neuron carrying the impulse up to the post-central gyrus. So ultimately, some fractions of a second after this has already happened, the brain hears the news. Oh my God, I felt something hot and I pulled my hand away from it. But that spinal reflex and the action has completely occurred before the brain ever knows that you got burned and that you've pulled your hand away from the hot stove. So this is called a spinal reflex, and we test spinal reflexes, and we know a map on the body. We know a map on the body of where all of the spinal nerves go. So here is a map. Use this one. Here's a map of what are called dermatomes. And dermatomes show you where each spinal nerve goes. So for instance, here at your belly button, we have spinal nerve T10. And T10 gives innervation there. Where your patella is L4. So if we tap on the patellar tendon and stretch the quadriceps muscle, L4 will send an impulse back to the spinal cord. There'll be a spinal reflex, which will send an impulse down L3 and L4 to cause the anterior quadricep muscles to contract and your knee jerks. So if a person comes in with an injury and we want to find out if their spinal cord is intact, we do deep tendon reflex tests. We tap on their biceps tendon, stretching C6 and T1. And we see whether or not the biceps contracts when we tap on the tendon. And that tells us that this portion of the spinal cord is intact. If we tap on the patellar tendon and we get a knee kick, we know that L3 and L4 of the spinal cord are intact. If we tap on the Achilles tendon and we get the soleus and the gastrocnemius to contract, we know that S3 and S4 are intact. So basically, we can test a little portion of the cord here, a little portion of the cord here, and a portion of the cord down there simply by tapping on tendons and demonstrating that spinal reflexes are intact. If the spinal reflex is intact, then we know that the spinal cord is intact in that location. Let me see if we're going to talk about dermatomes again in another lecture coming up, but let me see if there is spinal reflex example. Let me see if there's a video of that. I don't want any 5-minute videos on this. Let's try this.
Reflex action and reflex arc. Whenever we happen to come close to an object that is capable of harming us, we immediately withdraw the part of the body that is the most vulnerable. This is called reflex action. When a person touches a hot cup, the sensory receptors in the hand send a stimulus via the afferent pathway, which contains afferent neurons, to the spinal cord. The afferent neurons enter the dorsal nerve root of the spinal cord. The stimulus is passed on to the efferent neuron, which travels the efferent pathway to reach the effector organ, in this case, the muscles of the arm. As a result, the hand is quickly pulled back. The brain is not involved in the reflex actions, as it would take more time for the impulses to travel to and fro from the brain. The afferent neurons, or receptors, taking the causal stimulus to the CNS, the spinal cord. The efferent neurons, or effectors, the exciter neurons, and the action performed in response to the stimulus together form the reflex arc.
All right. Go back to where I can see you guys. Here we are. All right. Are there questions about this? Questions? I know you're all disappointed we didn't get to tap on somebody's knees. Oh well. All right. If there are no questions, then I'm going to stop and we'll be done for this day. And in 25 minutes or so, I will see half of you for a muscle lab. All right?
You are now
That's it.
unmuted.
All right. Have a nice
That's it,
weekend.
sir.
Yeah.
I'll coming back here.
What did I do for the morning lab? No, we're going to use the other link.
The lecture we used last.
The